about this problem. Which of the following functions f from r to r are onto and which are 1 to 1? Justify your answer. X squared, x cubed, e to the x. We're going to first recall some definitions. Recall that a function from the real numbers to the real numbers, and note that this definition could be very easily generalized to arbitrary domains and codomains, is 1 to 1 if for all x1 and x2 within the real numbers, if the two inputs are distinct, then the two outputs are distinct. So these functions map distinct inputs to distinct outputs, okay? And another way of visually seeing this on a graph is if you were to graph the function, then you would want the graph of the function to pass what's called the horizontal line test. So if I have a graph of some function and I draw a horizontal line, then if it intersects the function at two different points, well, what this tells me is that if this is my x1 and this is my x2, then notice that f of x1 is equal to f of x2 because they both are the height of this line. So both of the outputs are just the height of this line, and so these two inputs get mapped to the same output, and we would say that this fails the horizontal line test, and therefore the function is not 1 to 1. This is the more logical statement without just using graphic visualization. Now, if we go to the onto definition, function is onto if for all y and r the codomain, there exists an x within the domain such that f of x is equal to y. So, intuitively speaking, or on a graph, if I were to graph my function, then if I drew a horizontal line anywhere, the function would intersect the horizontal line at least one point. So if we look at our first function x squared here, then this is a very rough drawing, and look at the fact that, okay, first of all, x squared clearly fails the horizontal line test, so it's not 1 to 1, and it's also not onto because it doesn't actually reach any of these negative values. So its range is actually just the positive or the non-negative reals. And if I draw a horizontal line, at a negative number, it's not going to reach those negative numbers. But I don't want to prove these things graphically. We need to prove them a little bit more rigorously than using a graph. So let's do that now. Okay, so we already mentioned that it's not 1 to 1. How do we prove that? Well, to prove that this logical statement is false, we just need to demonstrate a counterexample, and it will automatically be false. So I need to demonstrate an x1. I need to find an x1 and an x2 such that x1 is not equal to x2, but f of x1 is equal to f of x2, okay? And if I find this example of x1 and x2, that is going to break the definition of 1 to 1 because this definition must hold for all x1 and x2 in the reals, okay? So let's even make this a little bit more rigorous. I'm wanting to introduce you to like these kind of math symbols, like the for all and the existence symbol, because I think that this problem is simple enough where it's nice to get some good exercise with these logical operators. So f is we're gonna argue. So my claim is that f of x equals x squared is not 1 to 1. Okay, so the proof is simply the following idea, if I take x1 to be 1 and x2 to be negative 1, then 1 is clearly not equal to negative 1, yet f of 1 equals f of negative 1, because these numbers squared equal 1. And so, but the logical statement, what have we just proven? What did we just prove? So, yeah, so I should say this is equal to 1, which is equal to f of negative 1. So we proved the logical negation of this definition. Okay, so we proved that this definition, the logical negation of the definition for all x1, x2 in R, x1 not equals to x2 implies f of x1 not equal to f of x2. Sorry, kind of running out of space in the whiteboard. Oh wait, I can just use my other whiteboard. Okay, let's see that. So x1 not equal to x2 implies that f of x1 is not equal to f of x2. Okay, so so this is the definition of being onto, and we proved its logical negation to show that it's not onto. So you can replace this logical operator with the word not. You can replace this logical operator with the word for all, and this is in, this symbol means in, this symbol means not equal to, this symbol means implies, and again, not equal to. Okay, so when I negate this statement, the trick is that the negation turns a for all quantifier into an existence quantifier, so there exists x1, x2, and then, and these need to be in R, such that, and then, yeah, so such that the same statement is now false. So the logical negation of this statement you can think of it as a P implies Q. So the logical negation of this is P is true and Q is false. So such that x1 is not equal to x2 and f of x1 is equal to f of x2. Okay, so this, there's no parentheses here. Okay, so I want to emphasize that this line here that I've just written is logically equivalent to the line on the bottom. I took the negation quantifier and I basically brought it inside the parentheses. Okay, so this is like the algebra of logic. So let me just, I think we can erase the statement of the question here. It's not that hard to remember. Let me just write this out in more abstract, let's just further abstract ourselves from the logic and write this claim in like P's and Q's, so logic notation. So if I look at the statement P implies Q, okay, then when I negate that statement, so here's my P implies Q, so the negation of this is, so I guess I should say, yeah, so this means that if P is true, then Q must be true. So I must demonstrate a P that is true and a Q that is false. And then I believe the and symbol is this symbol. Let me look it up for y'all so I don't get it wrong. That is correct. Okay, great. Yeah. So the negation of this P implies Q, the negation of P implies Q is just demonstrating a P that's Q and a Q that's false, okay? And so you can kind of imagine that these two statements are equivalent, or this statement is the negation of P implies Q, okay? So when I want to negate this P implies Q statement, I first need to bring the negation inside the for all. When I bring a negation inside a for all quantifier, it becomes an existence quantifier. Because to demonstrate that a statement that claims that something is true for all x1 and x2, you only need to demonstrate a single counterexample for this claim to be false. So essentially what I'm doing here is I'm bringing the negation quantifier inside the for all symbol. When I bring it inside the for all symbol, it becomes an existence symbol, and then I negate the P implies Q statement, and the negation of the P implies Q statement is P and not Q. So not Q is f of x1 equals f of x2. So there's a beautiful set theory logic going on here. So hopefully you can appreciate what the argument that I just explained. And if that is confusing, let me know in the comments, and I'll try to explain it better. Okay, but the proof itself, I kind of went into a lot of abstract logic stuff, which to be honest is not even really what I'm that great at. So don't take me too seriously, but take me kind of seriously, because I'm pretty sure I'm correct. Now, we've proven that x squared is not 1 to 1. We just now need to prove that it's not onto. Okay, so let's do it rigorously using the same approach. Okay, so we're going to negate this definition here. All right. So we know intuitively that it's not onto, right? Because we're not working in the complex numbers, we're working in the reals. So let's start here. So the claim is that f of x equals x squared is not onto. Okay, now instead of really thinking deeply about how to prove this rigorously, I'm just going to take the logical quantifier for what it means to be onto, and I'm going to negate that. So we need to show the following statement. Okay, so our claim is equivalent to the following claim in logic notation, that we're negating the statement that for all y in R, there exists an x in R such that f of x equals y. Okay, so to take the negation of the statement, I'm going to first bring the negation inside the for all. It's going to flip it to an existence. So this is there exists y within R such that for all x in R. So now I bring the logical negation inside of the existence symbol, and that flips it to a for all symbol. So for all x such that for all x within R, and then I negate the final claim. So negation of f of x equals y. All right, you see what I did there? I just brought the negation symbol past the for all on the existence quantifiers. When I brought them past these quantifiers, I flipped the for all to an existence, and I flipped the existence to a for all. Okay? And now, what is the negation of the logical claim f of x equals y? Well, that is simply the claim that f of x is not equal to y. Okay? So, this is the precise mathematical statement that we need to prove. Okay, so we need to find a y such that for all x within R, f of x is not equal to y. Okay, so let's choose y to be equal to -1. Okay, and then note that that f of x which is equal to x squared, is greater than or equal to 0 for all x in R. So, thus, f of x is strictly greater than y for all x in R, or in other words, f of x cannot be equal to y, right? We have the strict inequality, so we can never have equality. And there you go, okay? So we've demonstrated the existence of a y such that for all x within R, f of x is not equal to y. And now this is the precise logical claim that you have to prove. You do have some artistic flexibility when you write your proofs. Okay, every person has their own flavor, their own style of how they write things. Maybe you want to write a for all, like throw in a for all spice instead of writing the for all symbol somewhere. So here I wrote the for all in English rather than using a for all symbol. And you can always, everyone's going to have a little bit, that's obviously kind of a joke, but everyone has a little bit of flavor to their proofs, but it is important to identify the precise logical statement that needs to be shown in the proof. And there is no question about this. This is any proof of this claim here, f of x equals x squared is not onto, must boil down to proving this logical statement as true, okay? All right, so let's move on to the next x cubed and e to the x. Okay, so let's think about x cubed. In our minds, we have a picture of x cubed. It's like this function like this. So we actually know, intuitively speaking, that it's 1 to 1 and onto, okay? And of course that's not a rigorous proof, but it's important to have the intuition. And a lot of these proofs, especially at this level that we're going to go through, the textbook that we're going to go through, you need an intuitive guess or an intuitive picture of what you believe is true before you set about proving it, okay? All right, so intuitively speaking, we look at the graph of x cubed, it passes the horizontal line test, it seems to be onto because it's hitting everywhere on the vertical axis. Its image is the entire vertical axis, so it seems to be onto and 1 to 1. Now let's try to show that, okay? So let's claim that x cubed is 1 to 1. Okay, to show that, I need to show, so this is my equivalent claim, is that, well, x1, x2, x1 not equal to x2 implies f. Okay, so to show this claim, I'm going to use an interesting fact about x cubed, which is monotonicity, okay? And this fact that f of x equals x cubed is strictly monotone is actually kind of the intuitive reason why it passes the horizontal line test. So the reason why this function passes the horizontal line test is because it's strictly increasing. Okay, so strictly increasing means that x less than y implies f of x is x less than y implies f of x is still strictly less than f of y. And this is the definition of strictly increasing, okay? So notice that that x1, so notice that x1 not equal to x2 implies that x1 is less than x2 or x1 is greater than x2. Okay, because the real numbers have a complete ordering. They're actually, up to isomorphism, the only complete partially ordered field or something like this. Yeah, I think that's the correct terminology. So the real numbers have a complete ordering. So what that means is that any two elements have an order relation between them. So any two elements, if I take any two real numbers, they're either equal, or one of them is less than the other, or one of them is greater than the other, basically. Okay? So any two real numbers, because the ordering on the reals is a total ordering. Yeah, that's it. The real numbers are the only, up to isomorphism, the only complete totally ordered field. Correct me if I'm wrong, but I think that's correct. So the idea is that that we know that x1 is less than x2 or x1 is greater than x2, and then we can use this if we know that at x cubed is strictly monotone. So x cubed strictly monotone increasing. This will tell me that f of x1 is strictly less than f of x2, or f of x1 is strictly greater than f of x2, which is equivalent to saying that f of x1 is not equal to f of x2. So this holds for all x1 and x2 in R. So this completes our proof as long as we show that x cubed is strictly monotone increasing. All right, and so let's do that now. So x cubed is strictly monotone increasing. So if I have x less than y, how do we show that x cubed is less than, so y cubed? Well, if we assume that both of these are positive or non-negative, then I know that x is a positive number, okay? And y is a positive number. So I know that 0 is less than or equal to x squared, which is less than y times x. I'm allowed to multiply this I'm allowed to multiply these inequalities by x everywhere because x is positive. Okay? So since x is positive, I can multiply the inequalities by this. And then I can replace x on this right-hand side with a y. So I know that 0 is less than or equal to x squared is less than y squared because since x is less than y. Okay, so now we can just repeat the same process one more time and multiply this inequality by x, y squared x, and then y squared x. Since x is less than y, then this inequality, I can replace an x with a y to get y cubed, okay? So I get that, so this tells me that x less than y implies that x cubed is less than y cubed. But in fact, I don't need this assumption, okay, because I don't need this positivity assumption on x, as we'll see. So why is that? Well, essentially because we're cubing the relationship. So let me go ahead and erase this. Yeah, I'm going to erase this. So if x is less than or equal to 0 is less than y, this is a separate case that we need to consider, then if I cube x, the point is that if I cube x, I'm multiplying both sides of this equality by an x squared. Okay, actually no, I figured out a better way to do it without considering all the cases. So we could break it down into all the different cases like what I was about to waste my time doing, and look at maybe x less than or equal to 0 less than y, and then look at x less than y less than or equal to 0. Basically look at all possibilities of where the 0 could be. But there's actually a better solution, okay? So if I know that x is less than y, okay, then one thing I know about squares is that they're always positive. So I know that I can multiply this inequality by a positive number and it will be preserved. Recall that positive numbers, multiplication of an inequality by a positive number preserves the inequality. Multiplication of the inequality by a negative number reverses the inequality. So in order to multiply this expression by a number, I need to make sure that number is positive to keep the inequality sign. So in this case, I'm going to multiply both sides by x squared. And then since x squared is positive, okay, so since x squared is greater than or equal to 0, when I multiply this inequality by x squared, I get x cubed is less than y x squared, okay? All right, and now we're kind of, we're on a good track, because now let's look at y x squared, and let's compare this to y cubed, okay? So if I look at x squared and I compare it to y squared, okay? So how do I? Sorry, one second. Okay, I don't think this actually works. Yeah, this doesn't work. Okay, this doesn't work, but I feel like the start of this video was so good, or it felt really good to me. Like there was a lot of good topics that were covered. I'm just gonna keep recording, and yeah, this doesn't work because because x less than y, I wanted to replace this with a y squared, basically. But this does not imply that x squared is less than y squared, right? Because x could be like negative 9 billion, y could be 10, and then when I square it, I'll get x squared is a huge number and y squared is a really small number. So just knowing that x is less than y doesn't actually tell me that x squared is less than y squared. And so x squared could be huge, and then all of a sudden I have a problem because this right-hand side of this inequality is somewhat useless. Because I want to replace this x squared with a y squared to get myself y cubed, but I can't do that, okay? Because I don't know that x squared is less than y squared. So, okay, so what? So, okay, maybe I need your help a little bit here. See if you can help me solve the problem. But basically, yeah, I think what we're gonna have to do here, is we're gonna have to break this down into cases. So 0 is, okay, less than or equal to x is less than y. We already covered that case. Then if x is less than or equal to 0, which is less than y, then the key here is that x squared is positive. So I can use the same argument, okay? And notice that that x squared being positive implies that if x is less than or equal to 0, then x cubed is less than or equal to 0 times x squared, right? I can multiply just this inequality alone by x squared on both sides, and I get that x cubed is non-positive, okay? And so I get this inequality by multiplying this inequality by x squared, which is positive, and then here I get that since y is positive, y squared is also positive, so I can multiply this inequality separately by just y squared, and I get y cubed here. And so this tells me that x cubed is less than y cubed. Okay, do you see what I did there? So for this inequality, I multiplied by x squared, and for this inequality, I multiplied by y squared. And in both cases, I used the fact that x squared and y squared are positive. But I needed to kind of dance around the 0 to make this work, because if I didn't have the 0 there, then I'd run into issues. Like, I was trying to make things cleaner with the previous work, but I ran into a key problem. Okay. All right. So now let's look at the last case, which should just be x is less than y is less than or equal to 0. This will cover all the cases of where 0 could be with respect to x and y. And yeah, in this case, we will have right, so in this case, we're going to have x squared is actually going to be greater than y squared. Okay? So I can't multiply it there. This is the weird part. Okay, yeah, this is the hardest case, for sure. This is the hardest case. Oh yeah, no. Actually, okay, great. So what we want to do for this case is we do have x squared is greater than y squared. Right. Okay. Yeah. So, and then the idea is that somehow we get to here, x squared is greater than y squared, and then we can multiply this equality by x and y, multiply this side by x, multiply this side by y. Since these numbers are both negative, it's going to flip the equality one more time and give me this. So let's do it more rigorously. So let's multiply this inequality by x, let's say. So when I multiply this by x, since x is negative, it'll flip all the inequalities. So x squared is greater than yx, which is greater than or equal to 0, okay? Multiplying by a negative number flips inequalities. Okay, now, if I multiply by, now I want a y squared in here. So I know that x is less than y. So this expression, so I should have x squared less than y times x, and then I should actually be able to replace the x with a y here. Yeah, I think this is right. Sorry guys, I'm really struggling with this. I don't know why. This is just really weirdly hard right now. Okay. No. Okay. Yx. Y is bigger than x. Oh yeah, just multiply this. Okay, yeah. Sorry. So multiply this inequality by y. Multiply. So this is multiplying this inequality by x. So then if I multiply by y instead, I'm going to get yx, and inequalities flip again because y is also negative, y squared greater than or equal to 0, okay? Aha! So this tells me that x squared is greater than y squared, which is greater than or equal to 0. Okay, now if I multiply this inequality by y, again, it'll flip the inequalities. Anytime I multiply by y or x, it's going to flip the inequalities. Okay, so this is x squared y is less than y cubed greater than or equal to 0. If I multiply this inequality by x, instead I'll get x cubed is less than y squared x, which is, sorry, less than or equal to 0. Okay, we're on the right track. Okay, and now I need to somehow relate these two expressions to get my x cubed is less than y cubed. So to relate these two expressions, man, this is getting really hard. If I multiply this by y squared. Okay, if I multiply this original inequality by y squared, I get, and y squared is positive, so it preserves the inequalities. I get x y squared is less than y cubed, which is less than or equal to 0. Does that help me? Yes. If I look at these two inequalities, then I've just shown that y squared x is less than y cubed. Okay, great. Okay, now you just saw me stumble through a problem. Basically, this is how I would solve a problem if I wasn't, didn't plan out this lecture. These lectures are not planned, by the way. I'm just going up to the board and solving these problems. So I encountered kind of an obstacle, and I'm not sure how it's going to turn out on the video footage, but I guess we'll find out. Okay, so, but now that we've done this, we can actually write the proof, okay? So my claim is that x is less than y implies x cubed is less than y cubed, and the proof is what we already just did. So if x, so case 1, we had x was less than y, and both of these were positive, in which case we multiplied by x squared on both sides. And then we know that x squared, I can replace any x, since it's positive, I can replace x's with y, so this is less than y cubed. Right, because I can basically, x less than y is, I can multiply this by x on both sides since x is positive, so this is x squared is less than xy. And I can also multiply, let me just, we make it as rigorous as possible, okay? We need rigor here, okay? So 0 less than or equal to x less than y. If I multiply this, since x is positive, I can multiply this inequality by x, okay? That will tell me that 0 is less than or equal to x squared, which is less than y times x, okay? Now, I can also start with this inequality and multiply it by y, because y is positive. So it'll preserve the inequality, so 0 is less than or equal to xy, which is less than y squared. Okay, so what this tells me is that x squared is less than y times x, which is equal x times y less than y squared. So I get this chain of inequalities. Okay, and in particular, I get that x squared is less than y squared. And then I'm going to use this fact. So then I'm going to multiply this side by x squared on both sides, and I get 0 is less than or equal to x cubed, which is less than yx squared. And then I use the fact that x squared is less than y squared, and multiply this inequality by y on both sides, since y is positive, to get that yx squared is less than y cubed, which tells me that x cubed is less than y cubed. Okay, so that's case 1. Then case 2, we had x less than or equal to 0 less than y. This one is easier because I can just argue that x squared is positive, so I can multiply this inequality by x squared, and x cubed is less than or equal to 0. And then y is positive, multiply this inequality by y squared, and I get this is y cubed, like so. And so I still get x cubed is less than y cubed. There's my inequality that I want. And then in case 3, the most difficult one, which we were struggling through, we had x less than y less than or equal to 0. Okay, then I multiplied this inequality by x and by y. So when I multiply it by x, I get x squared is greater than yx is greater than or equal to 0, because I'm multiplying by a negative number. Similarly, when I multiply by y, I get xy is greater than y squared, which is greater than or equal to 0. So I might as well just include a y squared here. Okay, so this is what I have so far. And then, okay, and now I'm going to multiply this inequality, I'm going to multiply everything here by an x. So when I multiply everything by here by an x, since x is negative, it's going to flip the inequalities one more time. So x cubed less than yx squared less than y squared x less than or equal to 0. And then similarly, I'm going to start here again, but now multiply this by y. And again, y is negative, so it'll flip all the inequalities. So I get x squared y is less than y squared x is less than y cubed is less than or equal to 0. Okay, but I have x cubed less than yx squared less than y squared x, which is less than y cubed by this second line here. So, bingo. Okay? So what have I established? I've established the following claim that x less than y implies that x cubed is less than y cubed for any real numbers x and y, irregardless of their position with respect to the number 0. And so what this tells me is that since x cubed is strictly monotone increasing, then x1 less than x2 implies f of x1 is less than f of x2. Similarly, x1 greater than x2 implies f of x1 greater than f of x2. And if either of these are guaranteed to be true, so one of these is guaranteed to be true, and in either case, if I have a strict inequality, then I'm guaranteed lack of equality. So I have lack of equality here. So this tells me that f of x equals x cubed is 1 to 1. Wow, it took so long. Okay, so now we're going to prove that it's onto. Okay. Okay. Okay, so to prove that it's onto, I need to show this following claim, that that for all y in R, there exists an x in R such that f of x is equal to y. Now, we could just use the cube root, but that's kind of cheating, since like you can't just use the square root. I mean, in x squared, you can't use the square root. So why should you be able to use the cube root? It's kind of not obvious that the cube root is well defined yet. In fact, I don't even really like this question because honestly, this is way too hard of a question, believe it or not, because we haven't even built the real numbers yet. Like, this is the Foundations of Analysis textbook. We're going to be building the real numbers from scratch. And so this is kind of way too difficult of a question. We don't even have the right machinery to even answer this question, but regardless, we're going to answer it. And okay, so f of x is equal to y. So what are we going to do here? Okay, so basically the idea is I'm not going to use cube roots. I'm going to use the monotonicity. Okay, so we have shown that f of x equals x cubed is monotone, increasing. Okay, and then it's also continuous, and so I just need to show that it's not bounded, basically, in order to show this claim. Okay, so it is continuous. Again, we haven't even defined continuity yet, but we're going to take for granted that it's continuous. And the idea is that it suffices to show that f of x equals x cubed is not bounded above or below. Okay. And well, we know this is true because the idea is that a negative number, let's say negative n, if n is a natural number, then negative n cubed is negative positive n cubed, right? And so we know that n cubed is arbitrarily large. N cubed is certainly not bounded because n cubed is greater than or equal to n for all n within the natural numbers. The natural numbers are not bounded by the Archimedean principle, so n cubed is certainly not bounded. Therefore, negative n cubed is not bounded below, positive n cubed is not bounded above, and also by the principles that we're going to learn in calculus later on this course, we have something called the intermediate value theorem. Okay, so essentially, the intermediate value theorem tells me that since this function, so this function attains, let me just write this argument out for you a little bit better. So note that note that the sequence 1, 2 cubed is 8, 3 cubed is 27, n cubed, etc. And then plus or minuses everywhere. So plus or minus n cubed. All of these numbers are in the range of f of x equals x cubed. And so by the intermediate value theorem, to be proven later, f of x, okay, it's continuous by continuity. So continuous must take on all values in intervals n cubed, n plus 1 cubed, where n is in z. So n can be any integer. Basically, saying z is just saying positive or negative. So n can be a positive or negative number. So this function, which is continuous, we know it hits n cubed for all these natural numbers, and so by continuity, by the intermediate value theorem, it's going to hit all the values in these intervals because it hits the endpoints. Okay. So remember, the intermediate value theorem says that if a function hits at the endpoints f of a and f of b, if we know f of a and f of b, and it's continuous on this interval a to b, then it has to achieve all the continuous spectrum of values between f of a and f of b. Okay? So we know that x cubed will attain this continuous spectrum of values from n cubed to n plus 1 cubed for an arbitrary integer n. And then if we just further note that the union of these intervals where n runs over all the integers, so that's plus 0, plus or minus 1, plus or minus 2, plus or minus 3, etc., of these intervals, n cubed, n plus 1 cubed, is equal to the whole real line. Okay? So what that tells me is that since it takes on values on all of these intervals, then it must hit their entire union, right? It hits the entire union because any element in this union belongs to one of these intervals and therefore is hit by the function f. And so therefore the function f hits the entire union. But this actually forms a partition of the whole space as these sequences are unbounded, right? The sequence n cubed is unbounded in the positive direction. The sequence negative n cubed is unbounded in the negative direction. So these intervals actually form a partition of the whole real line, and therefore proving that the function attains all values on this, or surjects onto this union, is equivalent to showing that it surjects onto the entire codomain, which is to say that it's onto. Okay? So basically, let's write the proof explicitly here. And what I'm arguing here is that I'm not using the cube root. Now, Taylor probably wanted me to use the cube root, but I don't. It's just kind of gross. Like, I don't really want to use it. Okay, so to show this claim then, let's prove it. So we know that the union of n cubed, n plus 1 cubed, these intervals over n within z, is equal to the whole real line. So then if I let y be any element of R, okay, then y belongs to this union over the integers, these intervals. And therefore, y belongs to some interval of the form m cubed, m plus 1 cubed, for some m in the integers. But since f of m equals m cubed and f of m plus 1 equals m plus 1 cubed, and f is continuous, we know what? We know that there exists, by the intermediate value theorem in calculus, we know that there exists a value x within the interval m cubed, m plus 1 cubed, such that f of x equals y. All right, awesome. So that successfully shows that since y was arbitrary, y was an arbitrary choice, and for every arbitrary choice of y, we can demonstrate the existence of an x here by the intermediate value theorem such that f of x is equal to y. This proves by definition that x cubed is onto. Okay, and no cube roots were used, by the way. Okay, so let's move on to e to the x. So, e to the x. Now I'm going to get it very heuristic, because at this point, this is really just way I mean, we should be going to Papa Rudin if we want to start with e to the x. Like, this is just ridiculous. Asking this question about e to the x before we've even built the real numbers, before we even know what e is, we don't even know what the natural numbers are. This is a ridiculous question. It's completely not, we're unprepared to tackle whether or not e to the x is 1 to 1 or onto. We don't even know what e to the x is right now. But that's okay. So I'm pretty sure the textbook intended for this to just be like a calculus level proof, like not really a rigorous proof, because there's no way for us to even approach what this even means within our current framework. So I guess I'm not going to go in depth to this right now. I mean, I probably could. Like, there's probably no, okay, maybe there's a few people that have gotten to this point in the video. And if you have gotten to this point in the video, then, you know, I commend you. I commend you. I commend you. Let's look at e to the x, and let's just give a first level proof of why it's 1 to 1 and not onto. So it's clearly positive, so it's not onto. Since, well, why is it positive? Well, this is essentially definitionally, well, what is e to the x? What is the definition of e to the x? Yeah, so I mean, the definition of e to the x is it's the sum from n equals 0 to infinity of x to the n over n factorial. This is e to the x, right? But we don't actually know what this means because we haven't developed the framework for dealing with this. What this means is it's actually the limit of the sequence as, let's say, capital N goes to infinity, of the sequence of partial sums given by equals 0 to capital N to the n over n factorial. And so it turns out that this converges, you can use certain series tests, such as the ratio test. Namely, the ratio test is what you'd use. And if you did use the ratio test for any x, so if you let x be within R, and we looked at the ratio test, then we would look at a to the n plus 1, which is the value of the sequence divided by a to the n, okay? If this is, and I should say capital N here. Okay. All right, and okay, well, let's look at this. Well, this is just going to be what? Oh, no, I'm dumb. Sorry. That's wrong. We needed to just look at the terms. These are the a sub little n's. We need to look at the terms of the series and look at their ratio. So an plus 1 over an. And then this is going to be x to the n plus 1 over n plus 1 factorial divided by x to the n over n factorial. And now, bring the n factorial upstairs. This is just x over n plus 1, right? And x over n plus 1, for n large enough, this thing goes to 0 for all x, for all fixed x. Okay? So x is arbitrary, this thing will go to 0. It's x over n plus 1, which means that the ratio of these a to the n plus 1 over a to the n is going to 0. And what you conclude is that if their ratio like this is going to 0, then the idea is that you can somehow show that, well, you can show that this series, this limit must exist, so it's actually well defined. And then e to the x is well defined. And since you've gotten this far in the video, very few people are going to watch this far. I'd be surprised if anyone got this far. And since probably very few people are going to get this far, might as well just make it as rigorous as we can. We might as well just prove this in more detail. Why not? Why not? Okay, so Yeah, so we have this ratio test. We know that the ratio of a to the n plus 1 over a to the n goes to 0. So how does that mean that this limit exists? Okay, well, the real numbers are going to be Cauchy. So to show that the limit of the sequence exists, we might as well show that the sequence is Cauchy. Sorry, the real numbers are complete, which means that every Cauchy sequence converges. Wow, it's getting late. Okay, so I guess what I'm saying is if I look at the tail end of this series where I start at maybe at capital M, and go out to infinity, or I could call this not infinity yet, but capital M prime, let's say. So yeah, okay, so this is the idea to show that this limit exists is to show that the sequence is Cauchy, and if the sequence is Cauchy, since the real numbers are complete, then actually the sequence will be convergent. So to look at the Cauchy property, we're going to look at m prime, a to the n equals 0, minus the summation from n equals 0 to m of a to the n. Let's say m prime is bigger than m, so this is going to be the summation from m to m prime of a to the n, okay? All right, and then the idea is that, as we said, a to the n over a to the n plus 1 over a to the n is converging to 0. So how can we use this to our advantage? So since this converges to 0, I can choose a capital M large enough such that a to the n plus 1, let's say, is less than r times a to the n, is less than epsilon times 2 to the, sorry, 1 second. A to the n M. And then I need a 2 to the minus m here. Sorry, 1 second. My brain is like trying to make this work. Let's see. Why is the ratio test good enough? A to the n's with this is not pretty. Okay, so I think I can do this as 2 to the minus m. Yeah, choose an m large enough so that this works. Man, this is getting really rough. Okay, so then this would be replaced with a less than. No, that's useless. Ugh. Okay, wait, I think I can do this stuff. Okay, wait. Let's see. Summation, let's do k. K equals m to m prime of a to the k. Okay. Good, okay. So am plus 1 plus dot plus am prime. And then this thing is a m times 1 plus over a m plus a m plus 2 m plus 1 a m plus 1 m. Aha, yes, we got it. Okay, yes, am prime over am prime minus 1, am prime minus 1 over am prime minus 2, dot, am plus 1 over am. Okay, so this is the trick, is that basically if I pull out an am here, then this fraction becomes am plus 1 over am. The next term becomes am plus 2 over am, but I write it in this way, so I multiply and divide by a to the m plus 1. And then I know that all of these expressions, these a to the m plus 1s over am's, they're going to be less than some epsilon for m large. So then I can bound this by a to the m times 1 plus epsilon squared plus dot plus epsilon to the m, and m prime minus capital M, excuse me. And then if you send m prime to infinity, you're going to actually get an upper bound, which is the geometric sum, am, summation from k equals 0 to infinity of epsilon to the k. And this is the geometric sum. So this is am over minus epsilon, and epsilon is arbitrarily small, so just choose it to be less than 1. And now a to the m, a sub m, remember a sub k was just x to the k over k factorial. So now you just need to show that a to the m goes to 0 as m goes to infinity. And then you'll get that the sequence of partial sums is Cauchy, therefore convergent. And so, so now let's just send m to infinity real quick. And let's see here. So sending k to infinity, let's look at this expression. What happens if we send k to infinity? Well, again, we know that ak plus 1 over ak is going to 0. So ak better go to 0, right? Yeah, so if, for example, so this just tells me that a to the k plus 1 in absolute value, if this is true, this is telling me that a to the k plus 1 is strictly less than ak, and not only is it less than ak, but it's a to the k plus 1 is strictly less than 1 minus epsilon times a to the k. So just being strictly less than is not enough to convert to show that a to the k goes to 0. When you have a to the k plus 1 is less than 1 minus epsilon times a to the k, that's enough to show that the sequence goes to 0. So that completes the proof of the fact that this exponential function is well defined. Now that isn't a proof, that's just me acting crazy and doing a bunch of scratch work. So let me show you the proof from, based on all this scratch work. Let's just put all these ideas together real quick. So, okay. So we're going to define e to the x as the limit as capital N goes to infinity of the series x to the n over n factorial, where n goes from 0 to capital N. And then to show, okay, so we're working the real numbers, Cauchy sequences converge. So to show that e to the x is well defined, it suffices to show that the sequence is Cauchy. Okay, so then consider, so it suffices to show that this sequence x to the n over n factorial is Cauchy. Sequence of partial sums, the index of the sequence is capital N, which is the index of the final term of the summation, the length of the summation, okay? And so we're going to take, let's say the summation from n equals 0. Let's keep capital N, okay? X to the n over n factorial minus summation n goes to 0 to capital M x to the n over n factorial. So you need to show that this expression goes to 0 in n and m to show that the sequence is Cauchy. Well, let's evaluate this expression. This is just, I can assume without loss of generality that n is bigger than m, and then literally do the subtraction, and that's just going to give me a sum which starts at capital M and ends at capital N. And we need to show that this goes to 0 for large values of m independent of the choice of capital N. Okay, so what we're going to do is we're going to note that that x to the n plus 1 over n plus 1 factorial. This is the nth plus 1 term of the sum divided by the nth term of the sum over n factorial. This is equal to x over n plus 1, which is less than epsilon, where epsilon is chosen for n sufficiently large. And here I want to set epsilon to be strictly less than 1, otherwise this is kind of useless to me. So I'm going to set epsilon strictly less to 1, and then let me just make sure I have absolute values here. Okay, so this is just because of the Archimedean principle, which states that 1 over n goes to 0. So for fixed x, this inequality is a consequence directly of the Archimedean principle of the natural numbers, and so that tells me that I can choose an n large enough such that this fraction is less than epsilon for any choice of epsilon, but we're just going to set epsilon to be less than 1. It's kind of arbitrary here. And n sufficiently large. And so we're going to choose, okay, so basically we're going to choose and capital M such that M is our sufficiently large like quantifier such that anything greater than capital M we are guaranteed this inequality. And then so we're allowed flexibility in choosing the capital M, but we don't have flexibility in choosing capital N, because to show that it's Cauchy, we need to show that basically for M large, independent of the choice of M greater than M, for M large, this quantity is small, okay? So once I have this inequality by choosing M large enough, then I get this bound, so this is less than or equal to, okay, now pull out the x to the n term, and then we're left with, if we expand the sum, kind of what I did earlier, this is 1 plus x to the m plus 1 over m plus 1 factorial over x to the m over n factorial. So this is the first term, or I guess this is the first term of the series. This is the second term of the series. The third term of the series, just for clarity, x to the m plus 1 divided by m plus 1 factorial over, m plus 2. These are 2's now. We're at the third term of the sequence. And then I divide by x m plus 1 over m plus 1 factorial. And then I have x m plus 1 divided by m plus 1 factorial over here. And then x to the m over n factorial. So I've just pulled out an x to the m over m factorial and introduced this dummy term, which is the mth plus 1 term of the sequence on the numerator and denominator. So this term just cancels itself out. But in this using this dummy term, I can bound this term by epsilon and this term by epsilon above. Okay? So I can bound this term by epsilon squared. And similarly, I can bound the kth term of this sum by epsilon to the power k. So by the same logic, I have an epsilon plus epsilon squared plus dot 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 plus epsilon to the n minus m. Okay, bingo. And then this is going to be less than or equal to, just throw this out to be the full geometric sum, and that's 1 over 1 minus epsilon. This is less than or equal to x to the m over m factorial times 1 minus epsilon. And now we just need to show this quantity goes to 0 in capital M in order to show that the sequence is Cauchy. And to show this goes to 0 in capital M, it's not too bad because we already have this quantity here. So we already have this. So essentially, as I send m to infinity, let's just finish off the proof here. So sending m to infinity, Right. So now we're going to choose. Sorry, 1 second. So we're going to set m. We can choose m to be as large as we want. So we're going to set it to be some choice m naught, and then I'm going to add an m1, okay? So I'm fixing an m naught, and m naught I can choose it to be sufficiently large, m1 I can choose it to be sufficiently large. And the idea is that we know that x to the m naught over m naught factorial is a finite number, and we know that if I divide this m naught plus, x to the m1 okay, yeah. So we know that x to the m naught plus 1 over m naught plus 1 factorial divided by x to the m naught over m naught factorial. We know this is going to be less than or equal to x over, in absolute value, x over m naught plus 1. Okay, so now we're in business because, well, what can I say? Well, I can say for large enough m naught, this is going to be less than or equal to epsilon. It's the same argument that I made before. So now what I'm going to do is I'm going to say, okay, well, if I add m, if I do this inductively, then x to the m naught plus m1 over m naught plus m1 factorial divided by x to the m naught over m naught factorial. All right, this expression is going to be less than or equal to epsilon to the m1, okay? Why? Because it's the same trick that I did earlier, okay? Where basically I'm going to multiply this by, and this is for m naught large, not large. Basically, I multiply this by, I expand this fraction like I did before, where this is like x naught to the m naught plus m1 minus 1 over m naught plus m1 minus 1 factorial, and then I have the same expression upstairs in the numerator, x naught. So let me just write it out in the correct form. The product of a bunch of fractions, are x naught to the m naught plus k over m naught plus k factorial divided by x naught to the m naught plus k minus 1 over m naught plus k minus 1 factorial, where k will range from 1 to m1 minus 1. No, just range to m1. Where k will range from 1 to m1. This is going to be less than or equal to, well, each of these terms is less than or equal to epsilon because I've chosen m naught large enough. So each of these terms are less than or equal to epsilon for m naught large enough. So guess what? This entire thing is less than or equal to epsilon to the m1 as I claimed previously. So therefore, and this entire expression, all the cross terms cancel. If you expand this out in terms of the fractions, you get a telescoping product, and the telescoping occurs within the numerators and denominators canceling out, and what you're left with is this is just x to the, this expression entirely is just x to the m over m factorial divided by x to the m naught over m naught factorial. Okay? So all this goes to show, after you do the telescoping product and get it in this form, then you can rewrite this as less than or equal to x to the m naught over m naught factorial, epsilon to the m1, where epsilon is less than 1, times 1 minus epsilon, Now, finally, sending m1 to infinity, which is equivalent to sending m to infinity. Remember, m is equal to m naught plus m1. Then, as I send, it's better not put my video, dude. Yes. So as I send m1 to infinity, I'm sending m to infinity. Sending m1 to infinity sends this expression to 0 because epsilon is less than 1. And so this expression goes to 0 as m1 goes to infinity. Note that the expression m naught is a constant. Bada bang. So this proves that this sequence is Cauchy and therefore convergent for arbitrary x in the real numbers, which proves that e to the x is well defined. Okay, so now that we've defined e to the x, let's prove that it's not onto, okay? Well, oh man, this is just getting to be a little bit much. So I guess to prove that it's not onto, okay, honestly, I have to go right now. I'm getting a call. So I'm not going to do the rigorous proof of why it's onto. We've at least defined e to the x. It's not onto since it's, for example, e to the x equals -1 has no solution. As I pi is not a real number. Oh man, this is a crazy lecture. Okay. All right. Can we use this definition to show that it's not onto? Wow, how does one do this? How do you even show that it's positive? How do you show that it's positive? What the heck? This is crazy. The fact that this is always positive is just blowing my mind right now. Okay, yeah, no, this is outside of the scope. So basically, I'll just say e to the x is 1 to 1. Since it is monotone, since it is strictly monotone, x less than y implies e to the x strictly less than e to the y, and then so this property we would need to prove, and then it's not onto is just immediately follows from this property that e to the x is positive. So to show that it's not onto, we just need to show this property. To show that it's not 1 to 1, we would need to show this property. At this point, I've struggled enough just even defining e to the x. So at this point, I'm like, whoa, this is a little bit out of my pay grade, or it's just out of my time grade. I would spend more time on this, but I really have to go right now, so I apologize. Please, do the work that I have not yet done. Show me why is e to the x positive? Using this definition of e to the x, why is e to the x positive? Or use your own definition of e to the x. Show me why it's positive. Why is it always positive? And why is it monotone increasing? Why is it strictly monotone increasing? Because if we can show these two things, then we're in business, because then we'll have that it's 1 to 1 and not onto. But yeah, it's not even clear, it's not even obvious to me looking at this definition alone. Looking at this definition, it's not even clear. Neither of these are clear. Neither of these are obvious. If I take a really negative number, I'm going to have like an alternating series, which is going to be like some crazy alternating series. It's not even clear why that would be positive here. So yes, please enlighten me. Let me know. And yeah. If you made it to this far in the video, I am literally shocked and surprised. And yeah, go you. You're a beast. Appreciate you. Have a good night.